Hello. Did anybody see the total
Yes.
eclipse of the moon?
Yeah,
Was anybody impressed?
yes, I thought it was pretty.
You did? So
It was
I
interesting how long it took.
yeah, it took a long time. It took hours because the shadow of the Earth is bigger.
Yeah, which I didn't realize, and that was sort of the most interesting thing.
Yeah. Did you anticipate that it was going to get? Did you anticipate that it was going to be this color? Did you anticipate that it was going to take as long as it took? Did you anticipate that it was going to be as cold as it was?
Yeah, that I anticipated.
All right. So this is. Kurt just told me that while the eclipse was occurring, there was in fact a meteorite that hit the moon, and because the moon has no atmosphere, it hit the surface. So there is a new crater on the moon right there, and I guess somebody will go take a look with because there's still orbiting satellites, and there's always orbiting satellites orbiting the moon. So we're going to see whatever that looks like. But I was out looking at it, and I don't usually go to see the eclipse of the moon because I think it's not that interesting. And as it turned out, it wasn't. What was interesting to me was the fact that that the moon looks smaller to me than it normally does. Did anybody notice that it looks smaller? I mean, because I had a friend who told me it looked larger. So
It's supposed to look larger.
It's
supposed to. It was the largest moon,
Right.
Yeah.
largest eclipsed moon.
When it first came up,
Yeah.
earlier in the day,
Yeah.
it was very large.
So it looked large to you.
Very large. But then when I looked at it, when it was overhead, when the eclipse was happening, it wasn't very large.
Right. So that was the horizon effect of the moon. You know, the moon looks larger at the horizon. And they have a lot of theories, and I don't remember which one is the one that people like the best. But it's not like one theory that explains why the moon is larger. It's not larger. It's actually, you can measure it. It's not larger, but it looks larger psychologically.
I had a question about the color because when I was younger, I grew up in an apartment that faced east, and I remember just one night looking out, and there was this moon, lower in the horizon than this one was, blood red, but really blood red.
Right.
So I don't think that was an eclipse.
No, it was. It was.
But it was much prettier than that because it was lower and it was really red.
She saw it lower on the same day. She saw it lower. It was blood red, probably or getting blood red at that point.
But this was never blood red.
It was.
No, it was kind of a dark maroon. Look at it. It's
I know.
not blood red.
I know. You can make this blood redder. You can make
Well,
it redder.
I was standing there looking at it. It wasn't the color of the moon I saw when I was a kid, which was red.
Maybe your eyes were better. I don't have an explanation.
Okay, I'm just wondering if there's another reason the moon would turn red besides an eclipse.
No.
It doesn't have to do with the rays, the length of the
Yeah.
rays.
Or
So
that it was lower.
why does it turn red in the first place? It turns red because every sunset in the world is passing through the atmosphere of the Earth and ending up at the moon. So the moon is getting the red sunset of every piece of the atmosphere of the Earth impinging and hitting it.
But does an eclipse of the moon always have to be at the same time? This is beyond my astronomical.
Always has to be at full moon.
Right, but this was the moon rising.
You can get a full.
The moon was high.
You can get a full moon. Full moon. Remember, full moon is like all night long.
Right.
So
but-
from morning till night, the full moon, or from sunset to sunrise, the moon is full.
Right, but the eclipse
Can be any of that time.
So maybe it was a very early eclipse.
Yeah, think about this. When we were having an eclipse here, everybody else on the Earth who could see the moon was seeing the same eclipse
At different times.
at different times.
So they could have seen it lower.
So they could have seen it lower.
So it might have been redder.
No, it would have been more, it would have given the impression of being large. Because when the moon's low on the horizon, it always looks large. So it would have been a large, reddish moon, unexpected. Because you expect to see a white moon, and all of a sudden there's a red moon. So you go, what happened to
The
that?
moon I saw was not like that.
You know. And I'm not an expert on this.
Yeah.
What happens is I I'm an astronomer who never looks up. So when I hear that there's an eclipse of the moon, I don't bother.
Yeah.
Okay? But one of my friends called me and he said, "You got to see this." So I went out, and he sent me pictures of the moon that he took from his camera. Let me see if I can find it. It's really insane. My friend is quite a. I've known him since college. He's a civil engineer. You would think he would know some engineering, some science, but he's not a kind of person who really understands science in the same way that I do. And so what he did is he sent me pictures. So my friend Toby took pictures of the moon, and this is what he got. That's what he got.
Was that with an
With his
iPhone?
camera.
Oh,
With his iPhone camera.
That's what I got.
Right. Now that's because all of us think the moon is bigger, okay, than it is. You hold your iPhone up and you go, "Oh, I'll take that picture." It's not worth taking a picture of. It's small.
It also
You can
doesn't
cover it with your
register-
fingertip or a
It doesn't
dime.
register the color either on the
That didn't do the color either. But on the other hand, I had a friend who did.
Zoom in a bit, yeah.
What?
You
Well,
can zoom in a bit.
my friend Toby doesn't know how to operate his iPhone camera.
That's an engineer.
He's an engineer, right? But he's really not very good at engineering anymore. I mean, he's really a social engineer. That's what he does best. And for that,
He made you go outside.
right. But what does it look like? Come on, here. So look, with a regular camera with a telephoto lens, he was able to take this shot on the street, 75th Street. He was able to do this. That's not bad. That's not bad at all.
That's good.
Anyway, so the subject today is what I've been doing. I've been preparing a class, as I've told you last week, a class for the Amateur Astronomy Association of New York, and they have asked me to teach a class on what you can see if you look up in the sky down at the computer. And since I don't look up at the sky ever, case in point, this total eclipse of the moon, I'm an expert at what you can see looking down at the computer. So they asked me to do that. And let me see if I can find what I'm doing here. So there's so I'm preparing this website. I'm preparing this lecture, and in this lecture, I'm going to be referencing this piece of paper here on my computer. But you can reference it as well by going to tinyurl.com/Laird-astronomy-simulations. And if you go there, if you're busy and copy all that down, I'll try to write it on the board after class, you will be able to see this page. This page will tell you all the cool stuff that I have found that I want to show this class. And one of our people are taking a picture of that. So I know that's very good.
I'm gonna take it.
Right.
Easier.
Much easier than writing it down. Okay. So I have basically the universe was never as cool as it's been since the invention of the World Wide Web because there's so much stuff. So, for example, I'm just going to name a few of these things. Universe Sandbox, which costs $25. Starry Nights, Part of You, Uniview Theater, NASA Eyes, Solar System from NASA, Trek, NASA.gov, and Stellarium, and Solar System Visualizer, and Open Space, and Google Earth, and Google Earth, and Google Earth, and Google Earth, and Celestia. So we're going to do some of those. And the thing that I found, I got really excited this is yesterday when I discovered that I could do some really cool stuff right here on the screen and make it appear as if we are visiting any one of 4 different planets in our solar system. We can visit here. We can visit Vesta. We can visit Vesta and Ceres and the Moon and Mars. And not just visit, but we can literally explore it like we were hovering over it in a helicopter. So I think I'd like to go to Vesta just to visit for a few minutes. So Vesta is a minor planet of the solar system. It's one of the first asteroids that was ever discovered, and it was given the title of planet for a while until they discovered that there were lots of other asteroids, and so they called them asteroids. And Vesta was demoted from a planet to an asteroid. It never made the grade, but lost its position as a planet. This is partially because Vesta is really not round. Look at that. It is not round. That is the shape of Vesta. That is the shape of Vesta. Now, the thing is, how do I get such a great picture of this? Because a spacecraft spent over a year orbiting this minor planet. And in the process of doing that, it took 1 million pictures, I don't know how many, but a gazillion pictures, with a bazillion data points. And NASA took all those data points and created a 3D model, which your tax dollars have paid for, so I can do this and just move it any way I want to. This looks like it's the bottom is really weird, and the top is really weird, and geologists all over the world are writing hundreds of papers as to why all this is so. And look at the striations. You can see striations. Look at those striations here and here and here. What's that about? Well, I don't know the answer to that, but people are working on that. I think it has something to do. Actually, I don't remember what the reason is for that. I did remember once, but if I want to, I can visit this place. I can get closer, and I can look around like that. I can get even closer. What I want to do is I want to leave Vesta. Remember, what the topic today is not what I'm showing you. It's what I can show you. It's, gee, I've got the universe under my fingertips. That's the topic. So if you want to derail me and ask me a question about Vesta, that's okay, but that's not the topic. Okay? It's what I can do, showing you Vesta. That's the topic. Okay. So Vesta is one. I will show you Ceres in a second. Okay. Now Ceres is the largest asteroid, and the spaceship that went to Vesta was powered by an ion engine, and so it was capable of spending time around Vesta and then picking itself up and going to Ceres and then orbiting Ceres, where it still orbits. In fact, it's either is still in orbit or it crashed into it because it ran out of fuel. So it finally did its mission and came back. So this is Ceres. This is Ceres. Notice it's round. notice that it's larger, therefore, than Vesta. And because it's round, because it's larger and more massive, it was able to pull itself into a ball. Well, as they got closer and closer to Ceres, from long distance away, when they were, whoops, yeah. So I can't pull out any further than that, unfortunately, in this simulation. But as they got closer and closer to Ceres, they saw that there were two white spots on the surface of the planet. And they had no idea what it was, these white spots. And if you were in this class, we were here and speculating on what these two white spots were. Nobody had any idea what they might be. And then we got closer, and they turned out to be more than two white spots. And even more. And so the thing is, let's go visit these white spots in a way that no software has ever given me the capability of doing before. What I'm going to do is okay, so there's the white spots. Now I have a tool here, tools, and the tool is called Experience Trek Virtual Reality. And it encourages me to draw a path. So, hold on. It encourages me to draw a path. So I'm going to draw a path. I'll start here. And look, it lets me draw a path. So I'm going to draw a path that goes through this thing, through there, up to here, around and around, around, and maybe back right to here. Double click to finish it. Now, for those of you who have seen this sort of thing, it gives me that picture automatically. And that picture, I hold my iPad up, and my iPad recognizes that picture. Okay.
Why did it cast it before and now?
Let's not get into this.
Well,
I'd like to see it.
I'd like to see it. You just explained it. I don't know what we're doing.
Oh, what we're doing is we're fooling around with mechanical devices, and we're not getting anywhere. Is what we're doing.
Forget the mechanical devices.
No, the mechanical devices are the whole point of this lecture. Poorly organized as it is, I'm going to be trying to do this in a week and a half for a much larger audience. So,
Well, we'll have that Chrome.
yes, that will.
Can I ask
Yes,
a question?
please.
By walking around that white stuff on Ceres,
Yes.
can someone tell what it is? Is that matter left by an asteroid?
Yes, so, there we go. Here's the man. Okay, now, so while Kurt is taking us on a tour, Kurt, you can move it up and down and look and go left and right to just see what's going on. Okay, so that white stuff, okay, that we're now seeing on the tour, that white stuff turns out to be sodium carbonate, baking soda. Baking soda. How does baking soda get on the surface of a minor planet? It percolates up from below. Percolates up from below. Percolates? Percolates? What percolates? water percolates. Water has percolated up from below and deposited a salt on the surface of Sears. So guess what that says? It says that there is water below the surface of Sears. Sears, which we thought to be just an inactive asteroid that was just sitting around as is since the beginning of the solar system, has water that's busy. This is essentially, if you will, the lava of a water volcano from deep within the interior of Sears. And
Is it hot? Is it boiling?
it's hot enough to make it liquid. The 100 degrees centigrade is from freezing to boiling. Okay? So somewhere between 0 degrees centigrade and 100 degrees centigrade, the water exists somewhere down in the planet, deep enough for it to actually be coming up, and they've actually spotted geysers of water coming from Sears now that they looked.
And I was asking about the temperature.
Temperature somewhere between 0 degrees centigrade and 100 degrees centigrade. Right. Probably. Could be higher for that matter. It could be. But it's certainly liquid enough to carry the salt up through the cracks in the surface and whatnot. Isn't that amazing? So you can do this at home. You can visit Ceres or any of these other planets and do this with your viewer. This is a viewer. It's a small little thing you can carry it with you at all times and be able to play 3D games. And I'm going to give it to Kurt and ask him if it looks at 3D, like in 3D.
Oh, that's why it's a split
Series.
screen.
That's why it's a split screen, because he has two views. And I can't make this one screen. I've tried.
What is Ceres?
Ceres is a minor planet, 500 miles in diameter, more or
From
less.
just observation, how do you know it's salt?
I don't know that. I don't know that. I can tell you what I think, which is everything that reflects something absorbs some light and reflects other light. So if you look at the light reflected from the object and you use a spectrometer, which in fact that spaceship has, it will be able to tell you in what wavelengths it's dimmer and what wavelengths it's brighter, so it will have a spectrum. Let me see. Oh, made away. It went away.
It's okay.
Make it come back. Okay. Oh, the question that I'm trying to answer. The question I'm trying to answer here is does this look 3D? Okay. Because it's in fact, I have two viewers, but the question is, are the eyes separated enough for it to do the 3D thing? They can do that with data. They can literally, because this is all data. These are not pictures. This is data, and it's data. You have to know, it's data that is being transmitted to me from NASA as we speak. This data has been formatted for my pleasure from their database, and so they can literally give me a left and a right-eye view. But we don't see anything yet.
Yeah, we don't see it. Did this stop? Did your
I
application
didn't-
stop?
No, I'm there. We're on the screen.
There is my clock.
Does that mean it can have?
By the way, for those of you back out in TV land, that Kurt wrote the background software, which is basically telling you what the time is. It's 1:15, and that's Kurt's software. And what is the name
That's
of
a
the?
moon phase.
What's it called?
This one is called regular clock.
Regular clock, but your software is from Artware. What's
Hardware software. Yeah.
Artware software? Okay, so just in case. Anyway, so Kurt is
Still trying to get.
he's still
the
trying to
thing
do it.
right, but I think we lost it.
I think we've lost it. Okay. So we're going to give up on that. Right? I'm going to figure a way to stop it.
So what is the,
Okay, so what's the question?
well, what do we ascertain from this?
Well, what you ascertained that NASA, the thing that my point is that NASA's doing a really cool job of giving us something back for all the money that we've spent in taxes, which, by the way, is not a lot. I mean, we spend frightfully little on the space program, but they're giving us back. They've got this data, and they're giving it to us in the best possible way. I asked for this data. They gave me this data. They gave me a way to visualize this data. Thank you, NASA.
What does that tell us about Sirius?
I don't know what it tells us about Sirius. I do know that scientifically I'm more interested in being there, going there, having the experience of being there than I am about the science. I'm excited about the science. In fact, the sodium carbonate on the surface of Sirius, and that means that there's water underneath. I'm really thrilled. But the idea that I can personally put on a pair of 3D goggles and fly over Sirius, I don't know, and literally, just walk around, look around, you like the astronauts did, and of course, so there's the moon, and we can do Mars, and I'm going to do Mars.
Where is Sirius?
Where is Sirius? It's in the asteroid belt, and let's open another application that can answer the question, where is Sirius? Okay. Let's see. So I have all this software which does all sorts of great things. Let's see if one of these pieces of software can answer the question, where is Sirius, in a way that is most exciting. And I think the one that's most exciting is Universe Sandbox.
Can I take that just a second?
So Universe Sandbox. Oh, you want to take a picture of that? tinyurl.com/Laird -astronomy -simulations.
Yeah.
Okay.
Okay. Excuse me a minute.
Okay.
Thank you.
Okay. So I will start Universe Sandbox. Because remember, the question today is, what sort of games can we play with the universe? Places to visit. How can we visit the universe? Universe Sandbox is a piece of software which is designed for people who want to have their own personal universe. Because the word sandbox means essentially that if you're a kid and you want to play, you can make your own universe. It's a sandbox. They give you tools in the sandbox to add planets, to crash planets into one another. You can throw anything in this you want, but they start you off with the real thing. So let's see if we can see where Sirius is. And we can. Okay, so there's the Sun, Mercury, Venus, Mars. There's Vesta, okay, which is doing its thing there. Okay, there's Sirius. By the way, I don't know how to say it, whether it's Sears or Sirius. So one of those is correct.
Goddess is Ceres.
Sirius.
The goddess is Sirius?
Greek.
Greek goddess is Sirius. So I'm going to call it Sirius for the rest of the evening
Does
or
that
afternoon.
mean there's a possibility of life there?
Does it mean there's a possibility of life there? And the answer is yes. The whole thing, anytime, I didn't bother to say this because I thought it was at this point obvious. Anytime there's water, liquid water, everybody gets excited because the possibility of life is always there. There's liquid water on Sirius for 4.5 billion years. What do you think? Okay?
Well,
Possible?
Does it get a sun?
It doesn't need a sun. You can grow things at the bottom of our ocean where they have those tube worms and those shrimp and those crabs, and they're growing at the bottom of the ocean. No sunlight.
Well, how cold is it?
It's warm enough to have liquid water. That's how cold it is. Whatever it is, it's warm enough to have liquid water. Water is the universal solvent. It dissolves more things than anything does. It's really good for dissolving things like the chemicals that are needed to build up the DNA in our bodies. You can't build DNA without a liquid environment to provide all the building blocks to come together to make DNA. You can't do it in ammonia. You can only do it in water.
So it's not in the solar system
What's not in the solar system?
series.
No. Their series, this is the solar system. It's in the solar system. It's part of the asteroid belt. You can see, look, you see those little dots moving around with Ceres? That's some of the asteroids. So you can see the asteroid belt is moving around, okay? And there's Ceres, and there's Pallas, which is another of one of the 3 large asteroids. And we have Jupiter somewhere. I think Jupiter was in the picture, but now it's gone. So this is our solar system, and I can pull out. Look, see, I get more. I can tip it. It's fun. It's fun with solar systems. You can put it. You can put the Milky Way right there. You can move the Milky Way out of the way. This is I love this thing, and it's got a whole pile of built-in toys over here. Universe Sandbox. You see the thing called Workshop? You can basically throw in things into here. I don't know how, okay? But I know you can. I know you can crash planets together. I know you can do incredibly crazy things. So I'm just going to open the things that have been built before. But then I'm going to skip all the way to the bottom where crazy stuff is. Okay. So crazy stuff that people have built. Okay. Let's see. Crazy stuff that people have built. Oh, this is crazy. Somebody built Earth with a whole lot of moons, okay? And these moons are every now and then hitting each other, okay? So this is what you can do in this Universe Sandbox. It's crazy. You just set these things loose and they do things. They hit the Earth, they hit each other, they go flying off into space, obeying the laws of physics and gravity. Right? So, if you want to entertain yourself, yes.
This is all, there's something that you can play with and simulate, and I can see why some people would be attracted to it.
Right.
Does this same thing make available if we wanted to know what the Earth and the Moon look like in their own creation before, as opposed to adding new things?
Well,
Simulate that kind of
can we simulate with how the Earth and the Moon were created and that sort of stuff?
Happened, actually.
Now remember, the simulation is written by people who are more into the glory than into the physics. They work the physics as well as they can, but they're inventing this stuff, not really, because in order to do this stuff well, you need a supercomputer working days and weeks and months to come up with simulating the actual collision of 2 solid bodies together and what happens when that happens. Instead, what you're seeing here is it's happening in real time with my little $2,000 computer, and good stuff is happening, but it's not real. It's just fun. But they have made other simulations in which they've made more of an attempt to do that. Let's see, explosions. No. Earth and exploding moon. No. I guess I'm going to skip that. Let's just look at the normal ones. The normal ones are fun. This one is called the Parker Solar Probe. You know, we sent a probe to the sun, and somewhere in here there's a probe. It's on its way to the sun. Where is it? Come on, where are you?
Behind us.
Oh, there it is. Okay, there it is. It's on its way to the sun. Let's speed up time and see what happens. Okay, so there's the Parker Solar Probe. Passes by Venus purposely, and then goes close to the sun, and then out again, but it's going to go back again and come even closer and closer. It's not doing that very well. Okay, I'll stop.
Dizzy.
I got to stop this thing. Okay, so the solar probe was only made 1 or 2 passes. Point is, this software can do lots of cool things. I like collisions. So there's a moon called Mimas. Okay, now I'm sorry. So that is our moon colliding with another moon called Mimas, and you see the effect of that. Can we roll that over so we can see what it looks like over there? Yeah. Can I come in and see what's going on? Yeah. Is this real? No. But it does satisfy my basic need to play with the universe. Okay, so what other software can we do? I'm going to stop this one. Would you like to exit? Yes. Okay, so that was Universe Sandbox. Then there's Starry Nights, which Kurt and I bought together. Sharing software is illegal, by the way. I'm typing Kurt. That's not right. I want to Starry.
Why is it illegal?
You can't make money if everybody can.
I understand that part, but
It didn't-
how do you make it law?
Well,
How do you know
That's
if you're
another
sharing?
class.
there are various ways.
Copyright.
Oh, yeah, right, copyright.
Yeah, there
Different class.
are ways they can check. So they can literally see, because of the internet, they can see when I'm using their serial number on my computer and Kurt would be using it on his computer. They could tell that the two people are using the same copy at the same time. They can even tell that it's on a different computer and say that it's not okay.
That's free.
Right. But depending upon the software, they do or do not come after you. So Microsoft tends to be one of the more evil places where they really don't want you to share the software, so they don't really let you.
Sorry.
Okay, so this is one of my favorite ones. This is Starry Nights, and Starry Nights is generally doesn't do simulations of this nature very well. But what you're seeing here is I am flying past the moon. Yeah, so the astronauts, think of yourself right now as being on a spaceship that circled the moon. When the astronauts circled the moon, they saw Mare Orientali themselves with their naked eye as they passed by. But this is a flyby of the moon, it's not an orbit of the moon. So the astronauts didn't do this. Another simulation that they do, I made a list of simulations that are interesting. This is interesting, because most people don't know this unless you happen to be a shepherd, and none of us happen to be shepherds or astronomer. You either are a shepherd or an astronomer, and let's assume that you're neither of those. So favorite solar system, inner planets, Mars retrograde. That's what I'm going to do. So favorites, solar system, inner planets, Mars retrograde. Okay. This is Mars. Oops. Don't do that. This is Mars in the sky. if you are a shepherd, you see the sun. See, the sun moves across the sky. It circle in the sky once a year. But at night, sometimes Mars does that. Did you see what it did? It does something where it's going in that direction, sort of following the sun, and then it slows down. It goes backwards, and then goes forwards. Any shepherd worth his salt would know that Mars does that. And clearly Mars is going around the Earth, for clear, and Mars is doing this little thing. So in the old days, you have the Earth. Do I put the? So in the old days, you have the Earth there, okay, and then you have the sun here. It's going around the Earth like this, and then you have Mars, and it's going around the Earth like this. But you saw Mars was doing a thing where it turns around and goes backwards. So how do you make Mars go backwards? Well, what you do is you put Mars on what's called an epicycle. So you put Mars on a little circle like this. And this is Mars, and it goes around like this. Goes around like this. So while Mars is going like this, it's possible for Mars to be doing a backwards thing on this epicycle, so it can go backwards in the sky as you look at it. And that's how they accounted for Mars doing its backwards thing. And you go, oh, well, gee, that's really, you can say, well, clearly that's a lot of work to make Mars do that. Why don't they simply have the Earth go around the sun and Mars go around the sun, and you'll solve that, and you'll be able to get that backwards motion of Mars, because clearly you don't need the epicycles anymore once you use the heliocentric model of a solar system. Well, it turns out that while that's absolutely true, you still need epicycles. You just need fewer of them. So when Copernicus said, excuse me, the Earth goes around the sun, it wasn't completely obvious. The fact that they eliminated the epicycles, which you think would be sufficient reason to say the solar system got simpler because we eliminated the epicycles, we didn't. We just made fewer of them. What convinced Galileo that the Earth was going around the sun was he looked at Jupiter. He looked at Jupiter and he said, "Oh, there's some thing going around Jupiter. Something's going around Jupiter. If something's going around Jupiter, like, because nobody ever saw something like that before, if something's going around Jupiter, then gee, the Earth can be going around the sun." That wasn't convincing enough. What was really convincing was the fact that he saw Venus through a telescope. And Venus, when you look at Venus through a telescope, you should always see it in the crescent. You should see a crescent moon, crescent Venus. The only time you can ever see a full Venus is if Venus is on the other side of the sun. And I wish I had that here to demonstrate or draw. And I wish it was important enough for you to ask questions about, so I would draw it. But otherwise, I'll just leave it at that. Okay? The thing that convinced Galileo that the Earth was going around the sun was a non-crescent Venus, almost a full Venus, as you saw
You
it.
can see a full Venus when it's on the other side?
You see a full Venus on the other side of the sun. You can just think of the geometry. But when the Venus is on the same side as the sun as we are, okay, then it would be in crescent. But the only way, and if the Earth is, and if Venus is going around the Earth, you would always see it, and in a sort of a crescent way, especially if the sun is further out. Anyway, have to do that. I'd have to draw it, and we would.
Why
Yeah.
does the current view of Mars rotating around the sun, as Earth does, eliminate this curlicue or whatever it's called?
Why does it do the curlicule?
You said it solves it, it explains it.
Yes.
Why is that?
Okay, let me see if I can have a piece of software that answers that question. Okay. Hold on. I hear the question. Why does a heliocentric model of the solar system explain the retrograde motion of Mars? That's
Yes,
your question.
That's correct.
Right. And I'd like to find the answer to that in the software that I've got here, rather than drawing it on the screen. Okay? So let me see if there's something I can do within the confines of the fact that I'll bore you silly if I don't do it fast enough. Okay. Let's try this one. I'm going to go to Eyes on the Solar System. Okay. So NASA invented, part of NASA's gift to us all was to give us a gift of the solar system in simulation software. They gave us eyes on the Earth, eyes on the solar system. They gave us eyes on the Earth, eyes on the solar system, eyes on exoplanets. And what I'm going to do, theoretically we're out of time now, but we're not out of time. I'll show you if I can answer that question. Advanced. Okay, eyes on the solar system. Now, in this simulation, what we can do is, so there is our solar system. What we can do is I can click on any one of these objects, like the Earth. And with some luck, if I've got this right, I'll go there. Maybe not. Okay. Maybe I have to go, maybe I actually have to go there. Come on. Maybe. Nope. I don't think I can make this thing do it. I mean, some piece of software is bound to be able to do that thing instead of me drawing it on the board there. And I don't even have something to erase that.
What's that?
So
That's not an
oh,
eraser?
that's an eraser. Okay. Let's see if I can do that. You get points for that. Okay. All right, let's see if I can do this. So this is the sun. This is the orbit of the Earth. This is the orbit of Mars. And I will put the Earth here, and I will put Mars here. Because at any given time, they're at any place they want to be within these orbits. Mars takes 2 years to go around. The Earth takes 1 year to go around. So a year later, and here's the stars, because we're looking at Mars against the background of the stars. So I see Mars here against this star. Mars is going slower than the Earth, so as the Earth goes to here, Mars has only gone to here. So Mars is against this part of the sky. It has moved backwards.
I see.
As
It appears to.
appears to have moved backwards. When the Earth, so now it's a year later, okay? Earth is back to this point. Mars is over here, okay? Mars is over here. The Earth is back here at the starting point, but Mars is half an orbit away. And now as the Earth goes this way, Mars is going this way. So, in fact, they're going in the same direction. I think I'm screwing this up if anybody's paying
But
strict
theoretically,
attention.
it makes
If anybody's paying strict attention,
am.
I'm screwing this up, okay?
It's going in the same direction.
Right, but the question is, so that's the direction that Mars is in today. Tomorrow, Earth will have gone to here. Mars will have gone to this direction, and Mars will be moving in this direction. It will be against this part of the sky. So yes, Mars will seem to be going in this direction, whereas over here, Mars was seeming to go in this direction. I don't think I screwed it up. I think I got it
makes
right.
sense.
Right?
Last statement.
Right. So the this happens with all the outer planets. All the outer planets do this, and this would convince anybody who was willing to eliminate epicycles that the outer planets go around the sun, not the Earth, because you can't get this kind of motion without the epicycles. If you have the outer planets going around the Earth instead of the sun.
And going back to even before Galileo, when they didn't have telescopes, were people who were the shepherds, they would be able to somehow make some of these connections because they were looking at where the planets were in relation to the stars?
Right. Well, they still would. The idea of epicycles, okay, was an idea by Ptolemy. So way back thousands of years before. So the shepherds would be aware of the Ptolemaic system. Everybody thought that the sun and the planets went around the Earth. It made sense. Earth is stationary. It isn't rotating. Who would think the Earth is rotating? Right? That doesn't make sense. You don't feel it. So given that the Earth is stationary, how do you make sense of what you see in the sky? If the thing is going around the Earth and then it goes backwards, well, then it's got to be mounted on something that sort of spins around backwards a little bit, like an epicycle. So it doesn't take a big brain, once you've realized that it's going around the Earth, to concoct some way in which it manages to spin backwards for a while. Did I answer that question?
Yeah, no, I'm just, because some of these, I don't know, going back thousands of years, these people came to these really remarkable conclusions.
Right. Well,
Just by staring at us,
they knew,
studying the sky.
They knew certainly enough to know where the sun was going to, when the solstices would occur. You know, when the Earth. They knew when the sun would cross the equator on its way south. They knew when the sun would pass the equator on its way north. They knew when the sun would reach the maximum point in the sky. They knew those things in advance, and they built things like Stonehenge, you know, which definitely took a commitment, knowing the right direction to point the thing in. So they certainly knew that, and they knew that. I don't know how old Stonehenge is, but it's probably 7,000 years old, I'd think. So,
Something between 4 and 7.
yeah, right. So they knew that sort of stuff. Right. Let me just show you. I know the one that did the thing that I was looking for. Okay, it's the exoplanets one. Exoplanets. This one is interesting. This is eyes on the solar system again. The thing I like about this simulation is that in this simulation, it lets you go everywhere that you can see. So I will hopefully be able to click maybe the Earth, maybe not. Let's see. It says finalizing. I'm looking for that Mars answer still. But if I don't find the Mars answer, I'll be able to do one other thing that's quite good. Okay, there's the Earth. Okay. All right. This is. Is there any sound? I'm going to let this thing play because this is cool. If it's. Except there's no sound. I may have turned off the sound. I did.
Click and drag with your mouse to explore our galactic neighborhood and search for planets that might be hospitable to life.
Okay, so in this simulation, everything that looks like a star with its little cross like this is a star that has planets. So, and the other dots that you see are real stars, but they haven't been investigated or found to have planets. So everything you see here in this simulation is a star with planets, and every single one of these is a star that has one or more planets. And the best one of all is this one. Okay. This is a star called TRAPPIST-1. And TRAPPIST-1 is unique among all the stars in the sky that we have seen so far because of the story that we can tell each other about the solar system. There are 7 planets. This here, from here to here, is the habitable zone. The area of that solar system where liquid water could exist on the surface of the planet. Notice, in our solar system, there are 3 planets that are in the habitable zone. There's Venus, which really doesn't have liquid water on the surface of the planet because it's way too hot. There's Mars, has no liquid water on the surface of the planet because it's way too cold, and the Earth. So while there are 3 in our solar system that would be in our habitable zone, only one of them is anywhere decent for life. But these 3 could have water on the surface nonetheless. If there's water on the surface, here's the great story. Civilization could have evolved on each of these planets individually. And so, over the billions of years that this planetary system has existed, independent civilizations could have existed. And you know the story of the men from Mars invading the Earth? That's not real. But here, invaders from other planets invading other planets in their own solar system could be real. Okay? So that's why this is fascinating above all. That this is a place where life could have evolved 3 independent times. Yes?
How far is that star from Earth?
The nice thing about this, TRAPPIST, the nice thing about this simulation is it answers that question. I can answer the question, how long to travel there? And it says, at 60 miles an hour, it would take you 441 million years, okay? But they also answer the question at the speed of light, so as not to be so facetious. And in that case, the answer is 39 years. So it's 39 light years from the Earth. And the great thing about the software is they've got almost 3,000 dots in the sky, and they have an answer like this for every single dot. So let's go back and look at the sky and see what they've got. So that's the sky. We can just click any dot. I'll click this one over here. Kepler 270 is 3,324 light years away. Is it visible to the naked eye? Yes. How many planets does it have? 2. Okay? Compare with our solar system. So let's compare with our solar system. So that's Kepler 270. That's the 2 planets. And that is our own solar system, where Mercury and Venus and the Earth's orbit. So every one of these 3,000 planetary systems, has a picture like this that they can show you. Yes?
We talk about the habitable zone
Right.
being a certain distance from whatever the star is for life, but you've said other things that contradict that.
I've said nothing that contradicts it. It's
Does habitable mean just for what we think we can live on, or does habitable mean possibility for life? And if it's possibility for life, then we know it might be on an asteroid or someplace much further out, because it may be frozen on the surface, but there may be something inside.
Habitable.
So habitable means what?
Okay.
Life or us?
habitable by no means means us. Habitable does not mean us. Okay? We are, it means anything that's growing in our gut is also qualifies as habitable. And it happens to be growing in our gut. But if it could be growing on a pond, if it could be growing on a glacier, if it could be growing at the edges of a volcano, if it could be growing at the bottom of the sea, if it could be growing 3 miles deep inside of a rock, habitable. Anything that is life, period, qualifies as habitable. We are special. So intelligent life is much by factors of tens of millions less likely. The question is life itself likely or not likely? Does life originate every time it can, or does it require special circumstances of which we are the end point of evolution, but perhaps we ourselves, okay? Life has been around for 4 billion years on this planet. For 2 billion years on this planet, life was singular celled. When life became multicellular, it took over another 2 billion years for life to get to be multicellular, and then in the last 500 million years for it to start to concoct things that left fossil evidence, like skeletons, bones. But it took 4 billion years of doing nothing special. Half that time single-celled, half that time multi-celled, and then us. Okay? Is that a series of accidents that would not occur in the universe ever again, hardly ever? Or is it in fact something that occurs all the time given that there's enough time? Does life do this, make us, every single time it can? Or does it simply make life every single time it can? Or does it never make life, even if it can, because it's really too hard and we were just some sort of cosmic accident? We don't know any of those questions.
So
The answers to that.
The habitable zone doesn't.
Yes.
Habitable for us is really basically what you're saying, something that evolved. Because at the same time, you were saying that if there's water, then there's a possibility of life.
If there's water, there's a possibility of life.
Below the surface.
Could be below the surface.
So that a habitable zone would extend much further away from a sun.
So the habitable zone would extend much further away from the sun. And you're absolutely right, because this business of the habitable zone, it's bullshit. You're right. It's bullshit. Anywhere there can be liquid water, it doesn't have to be in the habitable zone, because Ceres, which I told you, Ceres, which I told you has liquid water below its surface, has a possibility of life down there because in fact there's liquid water. So this business about the habitable zone is really just for amateurs. You're the professionals. We don't need to do that. We don't need to talk about habitable zones any longer. And I think we've run out of time. So, and before you run away, there's an attendance sheet. So please, those who have to leave earlier, raise your hand. I'll hand this sheet to you. Yeah, here. I'll give it to you.
Could you
Thank you all.
put that site back up?
Oh, yeah. Oh, and please note, as I'm passing around the attendance sheet, that there is dates on the attendance sheet which tell you that I'm going to be gone for certain periods of time, and it says it on the attendance sheet.
You're going away?
My daughter's giving birth in Turkey. So yeah.
Wants a Turkish baby.
Right.
That's not nearby.
Right.